Aloha BIOCHEM. In this lecture we continue on in chapter 1 and we do some problem solving. Hello! So we're getting pretty far into chapter 1 now. You can see the outline. Today we're going to hit some problem solving. A lot of this is covered in sections 1.7 and 1.8. So I've written several examples here, and we'll just go through the examples. I think there are 5 examples in this video. So the first one. The diameter of a healthy red blood cell is approximately 8.0 micrometers. That's the micro prefix. Convert to meters and express the answer in scientific foundation. That should say scientific notation. So red blood cell's diameter is 8 micrometers. Convert that to meters and report the answer in scientific notation. So I'll show you a picture of a healthy red blood cell. There you go. So there's some red blood cells right there. They look like little donuts almost. Kind of cool looking. So the diameter is basically from this distance to that, going all the way across. That's about 8 micrometers. Too small to see. We would need a microscope to see it. Now, to convert micrometers to meters, it helps to know what a micrometer is. 1 micrometer is 10 to the negative 6 meters. In other words, it's a millionth of a meter. I'll remind you where you can find information on these prefixes. It's table 1.2 in your textbook. So table 1.2, the micro is a millionth. So it's 0.000001 meters, or you could say 10 to the minus 6 meters. Okay, so the relation between micrometers and meters is written right here, and we are going to convert from micrometers to meters. The way you do a calculation is you take the measured value that you start with and you put that on the left, and then using the relation you build the conversion factor. Now we want to get rid of micrometers, so we put this side on the bottom, and we want to convert to meters, so we put that side on the top. And remember how this works. This is the same distance upstairs as downstairs. 1 micrometer is the same as 10 to the minus 6 meters. So when you multiply by a conversion factor, it's like you're multiplying by 1. You're not changing the actual measured value, but you will be changing the units. So handling our units separately from the numbers, micrometers times meters divided by micrometers. And the micrometers cancel, and we're left with meter, which is what we were looking for. And then 8.0 multiplied by 10 to the minus 6 divided by 1. Well, you don't have to divide by 1. It doesn't do anything. 8.0 times 10 to the minus 6. That's actually already in scientific notation. Remember, scientific notation numbers have a number between 1 and 10 multiplied by a power of 10. And that's what we have. So this is the answer, 8.0 times 10 to the minus 6 meters. The next example, weight of a hemoglobin A protein molecule is 1.07035 times 10 to the minus 13 micrograms. So that's the mass or the weight of this protein molecule. Convert that to nanograms and atomic mass units. So you're given a mass. This is the mass of a certain protein molecule, and you're asked to convert that mass to both nanograms and atomic mass units. And before we do that, we'll take a quick look at a hemoglobin protein molecule. I got a few pictures for you. Hemoglobin is the main protein inside of red blood cells, by the way. So remember those red blood cells? Well, if you take a little closer look at one, red blood cell, if you dehydrate it, if you get rid of all the water inside, then 96%, like 95% of the dry mass would actually be these hemoglobin protein molecules. Okay? So hemoglobin proteins are the stuff that makes up red blood cells for the most part. And what they do is their job is to carry oxygen from the lungs and distribute it throughout the body. So here's another representation of a hemoglobin protein molecule. There are lots of atoms in there. And, the red ones are oxygens, the white ones are the hydrogens, and the black ones are the carbons. And you might see a few other. That looks like a sulfur back there, a yellow one. And anyway, so hemoglobin this big molecule, here's another representation of it. If you don't want to look at all the atoms, if you just want to look at it as like a blobby structure, there it is. Now what you can't see is these atoms are attached together in a long chain. Okay, and that chain is kind of all just collapsed together. It's all crammed together. So it looks kind of like that. But if you were able to see the actual chain, what it does, it looks kind of like this. So, this is an artistic representation. It kind of coils around sometimes, and proteins do this. They have these interesting helical shapes, and they're very cool looking. So here's another representation of hemoglobin protein using that artistic drawing. And so inside the protein there are these places called the heme group, and that's where the oxygen molecule attaches. So what happens is your red blood cells have these protein molecules inside of them, and when oxygen diffuses into the cell, it sticks to this large molecule, and there's 4 places for it to stick to. Okay, so here's kind of what happens. You have these red blood cells and oxygen molecules in the lungs when you inhale, and the molecules go into the cell, and they come across these proteins, and they attach at one of those 4 locations. Okay, so that's a little interesting background on red blood cells and hemoglobin. So let's go back to the problem. The weight of a hemoglobin A protein molecule is 1.07035 times 10 to the minus 13 micrograms. Convert this mass to nanograms and atomic mass units. So what is a microgram, and what is a nanogram, and what's an atomic mass unit? You can find this information in your textbook. I'll point you again to table 1.2. So there it is. This is a list of the common prefixes that you might need to know about. A microgram is a millionth of a gram, and a nanogram is a billionth of a gram. So a microgram, that's that part of a gram, and a nanogram is that part of a gram. So if you use powers of 10, a microgram is 10 to the minus 6 grams, and a nanogram is 10 to the minus 9 grams. Now, an atomic mass unit is not listed in this table, and so I'll explain what that is when we do that part. So, remember, when you convert measurements, you put the measurement on the left and you multiply it by the appropriate conversion factors. And that gets you to the units that you're looking for. So, starting with the mass in micrograms, remember 1 microgram is 10 to the minus 6 grams. We could also say that since a microgram is a millionth of a gram, it takes 1,000,000 micrograms to equal 1 gram. So we could use this relationship between micrograms and grams, or that one between micrograms and grams. Both would work. The textbook shows you this, but you should also realize that you can write it that way. So we can take our micrograms, our measurement in micrograms, and then using the first conversion, the first relation to build a conversion factor, we put this part on the bottom to get rid of the micrograms, and we put the grams on top. So working our way through the calculation, the first conversion factor gets rid of micrograms and gets us to grams. And now we can use a second relation between grams and nanograms. 1 nanogram is 10 to the minus 9 grams. If you go back to that table, that's what nano means. If you have a nano, that means you have 10 to the minus 9. So a nanogram is 10 to the minus 9 grams, or a billionth of a gram. So since we've gotten rid of micrograms and we've gotten to grams, now we want to get rid of grams and get to nanograms. So put the grams for this relation on the bottom and the 1 nanogram on top. So you see, this is a two-step conversion. We take our mass in micrograms, and the first conversion factor gets rid of micrograms, gets us to grams, and the second one gets rid of grams and gets us to nanograms. So when you do unit conversions, make sure that you have these, you don't have them flipped the opposite way around. So, check your conversion factors. Yes, 1 microgram is the same as 10 to the minus 6 grams, and yes, 1 nanogram is the same as 10 to the minus 9 grams. So now let's do the math. We handle our units separately, so microgram times gram over microgram, that cancels the microgram, and then times nanogram divided by gram, and that cancels the gram, and we're left with nanogram. So those are the nanogram units at the end. And now do the math for the numbers. 1.07035 times 10 to the minus 13 times 10 to the minus 6 divided by 1 times 1, and then divided by 10 to the minus 9. So since you have a lot of powers of 10 here, and you're taking 10 to the minus 13 and you're multiplying 10 to the minus 6 and you're dividing by 10 to the minus 9, you remember the rules for multiplying and dividing with powers of 10? When you have two powers of 10 and you multiply them together, you add the exponents. So 10 to the minus 13 times 10 to the minus 6, you would take 13 plus negative 6, or just 13 minus 6. And then when you divide by a power of 10, you subtract that exponent. So since we're dividing by 10 to the minus 9, we're going to subtract negative 9, and that would just be like adding 9. So the answer would be 1.07035 times 10 to the minus 13 plus negative 6, and then minus 9, or plus 9. And now it's easy to combine the negative 13, negative 6, and 9. That comes out to negative 10. And so the mass is 1.07035 times 10 to the minus 10 nanograms. Check. Now for the second part, to convert to atomic mass units. This is what an atomic mass unit is. This tells you the relation between atomic mass units and grams. Now, atomic mass units are used a lot in biochemistry and chemistry, and they are very, very, very tiny amounts of mass. In fact, it takes this many of them to equal 1 gram. That's how small they are. So they're much, much smaller than nanograms. It takes 10 to the 9 nanograms to equal a gram, and 10 to the 6 micrograms to equal a gram. But look how many atomic mass units it takes. 6.022140 times 10 to the 23rd atomic mass units equals a gram. So these are way smaller than either of those. So this is the relation between grams and atomic mass units. And doing the same sort of method, we can take our measured mass, convert from micrograms to grams, just like we did up here. And in this one, I've decided to use that other relation. So either one of these would work. So although I used the first one in the first calculation, I'm deciding to use the second one in this calculation. So to get rid of micrograms, we put this part on the bottom because we want to get rid of the micrograms, and we want to convert to grams, so we put that part on top. All right? And now, doing the calculation, after we go through the first conversion factor, we now have grams. So now we can use the relation over here to get from grams to atomic mass units. So to get rid of grams, we put that on the bottom, and we put that on the top, and that gets us to atomic mass units. Doing the calculation, micrograms times grams divided by micrograms, that gets rid of the micrograms, then times atomic mass units divided by grams, and that gets rid of the grams, and we're left with atomic mass units. And then we're left with atomic mass units. And then the numbers, 1.07035 times 10 to the minus 13 divided by 10 to the 6 multiplied by 6.0221408 times 10 to the 23rd. So I would probably take, since you can do multiplication and division in any order, I would take this number and multiply it by that number, and that would give you 6.4457981, and then do the powers of 10. Okay, 10 to the minus 13 divided by 10 to the 6 multiplied by 10 to the 23rd. Okay, you see what we're doing? When you take this whole number right here, you divide by that one. You can ignore the ones, and you divide by that one, and you multiply by that one. You can separate the power of 10 parts from the number parts. So I took the number parts and I multiplied those two together, and that gives us that. And now the power of 10 parts. 10 to the negative 13 divided by 10 to the 6 multiplied by 10 to the 23rd. And using the power of 10 rules for multiplying and dividing, when you divide by this one, you're subtracting 6. So it's 10 to the minus 13, and the exponent is negative 13 minus 6. And then when we multiply by 10 to the 23rd, we add that 1. So minus 13 minus 6, that would be negative 19, plus 23 would be 4. So all of this simplifies to 10 to the 4th. So here is the answer in scientific notation. You have a number between 1 and 10 times the power of 10. But, I would probably not put this in scientific notation. So I would get rid of it. Since it's 10 to the 4th and you want to get rid of the scientific notation, you would move the decimal place over to the right 4 positions, and it would go right there. Now notice how when we first reported the answer without simplifying it yet, we had extra digits. The 841 was rounded out. So we started with 6 sig figs, and therefore we need to end up with 6 sig figs. So that's 1, 2, 3, 4, 5, 6. So we got to round it right here. So it's going to round up. So 79 would become 80, and there you go. Okay, it's kind of an involved problem. Next problem, a patient. You guys are going to be dealing with lots of patients later on. A patient is prescribed 1.25 grams of amoxicillin, which is some antibacterial drug, I believe. Okay, amoxicillin, which is available in 250 milligram tablets. How many tablets are needed? So you want the patient to take a combined total of 1.25 grams of amoxicillin, but it comes in these tablets, and each tablet has 250 milligrams. So how many tablets does it take to equal 1.25 grams of the drug? By the way, amoxicillin is a very closely related drug to penicillin. And I'll show you a picture of amoxicillin and also penicillin. So here's a molecule of amoxicillin. So you can see the carbon atoms are the gray ones, and the hydrogens, the white ones, the oxygens are the red ones, and the blue ones and the nitrogens. I think that's a sulfur right there. And so anyway, it's kind of a complicated drug molecule. Okay. Now penicillin has very similar looking structure. So here's amoxicillin. Let's look at penicillin. Okay, you see the difference? There's penicillin. Amoxicillin, it's been kind of rotated a little bit. So here's amoxicillin, and then if you kind of swing this portion down, there it is again. The only difference here is amoxicillin has this extra oxygen hydrogen right here attached. So instead of just hydrogen, it goes oxygen hydrogen. Okay, I believe that's the only difference. So a lot of times drugs are like that. If you have one drug, penicillin's been around for a long time. A miraculous drug, and sometimes it doesn't quite work, I guess. And so what people do is they just alter the molecule a little bit and synthesize another drug which is just like it, and maybe it works a little bit better, maybe it doesn't work as good, and so that's drug design. People do that all the time. So here's your amoxicillin. All right, and I'll show you another representation of amoxicillin. So you'll be looking at more of these later in the semester. So this is amoxicillin. It's called the skeletal structure. If you want to draw molecules, it's kind of a complicated looking molecule. And there's the ball and stick representation. So these represent the same molecule. Okay, there you go. All right, so you can hear my cat in the background. That's Spike again. I think Spike wants to get back in the video. A patient is prescribed. Okay, so we've already read this. How many tablets does it take to make 1.25 grams? Come here, Spike. Let me get in the video, Spike. Here you go. Here you go. We got all these birds outside. I think Spike wants to go outside and see if he can get one. So, all right. Spike, let's learn about amoxicillin first. Okay. Maybe that'll shut him up for a little bit. Okay, so this is the mass of the drug that we're starting with, and we want to figure out, the question is how many tablets. So we want to figure out how many tablets. Now, let's see what the problem tells us. One tablet contains 250 milligrams of drug. So if you're talking about a tablet, then that means you're talking about 250 milligrams of amoxicillin, right? So you can kind of equate them. I know over here this is mass and that's tablet, so it's not like you're converting, this is converting between units of the same type, but still, one tablet is the same thing as 250 milligrams of drug. So if we can figure out how many milligrams of drug the patient's supposed to get, then we can use this to get to tablets. Well, we can do this because we're told how much drug in grams the patient is supposed to get, and we know how to get from grams to milligrams. 1 gram equals 1,000 milligrams, or more equivalently, 1 milligram is 1,000th of a gram. Okay, either one of these would work. So take the mass of amoxicillin, put that on the left, and then using the first relation to build a conversion factor, we get rid of grams by putting that on the bottom and get to milligrams by putting that on the top. And now we've gotten to milligrams. And then we can go from milligrams to tablets by using the second relation, which was given to us in the problem. So the second relation says 250 milligrams is the same thing as a tablet. That's how much is in a tablet. And so now you get rid of milligrams and turn it into tablets. So doing this all together, the units, gram times milligram over gram gets rid of milligrams, times tablet over milligrams gets rid of milligrams, and you're left with tablet. For the numbers, 1.25 times 1,000 divided by 250. And that comes out to 5. So you might say, well, it should be 5.00, because that's, 5.00. We had 3 sig figs over here, and that's exact number, and 3 sig figs right there. So we should get 3 sig figs. This should be 5.00. But tablets come as whole tablets. You either have one or you don't. So if you need 1.25 grams of tablets, if 5 tablets doesn't get you that much, then you're going to get 6. So the answer is either going to be 1, 2, 3, 4, 5, 6. It's going to be a whole number of tablets. So it turns out that when you do the calculation, you get 5.00, but so that's 5 tablets will get it for you. So hopefully that makes sense. Now the last, this is not the last problem, 2 more problems. The last 2 problems deal with acetaminophen, also called paracetamol, which you'll find in Tylenol, my favorite headache medicine, and show you paracetamol right here. This is, so sometimes you'll hear it as paracetamol, or sometimes acetaminophen. Okay, either or is the name of the drug. Now, here's the ball and stick model. It's a simpler molecule, and it's pretty good at getting rid of headaches, pain reliever. And there is the skeletal representation. So you see the relation. So we'll figure out how to draw these later. Don't worry about how to draw those, but just showing that you what you're going to be doing later. All right. Now, so there it is. Here we go. A dose of 240 milligrams acetaminophen is prescribed for a 20 kilogram child. how many milliliters of children's Tylenol, which is 80 milligrams of drug per 2.5 milliliters, are needed. There's a lot of information in this problem. A dose of 240 milligrams of acetaminophen is what you want the child to get. Now it tells you it's a 20 kilogram child, and you might be thinking, well, maybe I have to use this in the calculation somewhere, and it turns out you don't. You have to use this. So just because a number is given to you in the problem doesn't mean you're going to use that in the, to solve the problem. This is just a dose of acetaminophen is prescribed for a child. How many milliliters is needed if you get 80 milligrams of the drug in 2.5 milliliters? So if 2.5 milliliters of the syrup contains 80 milligrams, then how many milliliters do you need to give the child to give them 240 milligrams? Okay, so maybe you can see, how to do it, but let's write down the relations that we know about. So we're trying to take, if we need 240 milligrams of drug, then how many milliliters of the children's Tylenol syrup does that require? So we want to turn this and figure out, how many milliliters of that does it take? And in the problem, it says, well, 80 milligrams of drug is what you get from 2.5 milliliters of the syrup. And so really, this relation can get us directly from milligrams of drug to milliliters, because look, we have a relation. It's given to you right there in the problem. Milligrams of drug, 80 milligrams of drug is what you get from 2.5 milliliters of syrup. This is like an equals. If you have 2.5 milliliters of syrup, that means you have 80 milligrams of drug. So they're basically equal to each other. And you can use this relation to build the conversion factor. All right, so starting with your 240 milligrams of drug, we want to get rid of milligrams and turn it to milliliters. So using this relation, you get rid of milligrams, you put that on the bottom, and you turn it to milliliters, so you put that on the top. And that'll do it. So milligram cancels milligram, and you're left with milliliter, and then 240 times 2.5 over 80, that gets you 7.5. So that's how many milliliters you need. And you look at one of those cups, and so you fill it up to the 7.5 mark. So the next problem is another similar problem, also involving acetaminophen and children's Tylenol. It's a little more tricky, this one, I think. So I liked the last one. I think I got this in our textbook, and so I wrote another one that was closely related to that, but it contains a little catch. All right. The question is, how many milligrams acetaminophen are contained in the dose of children's Tylenol shown to the right? Okay, so how much acetaminophen is in this cup if the medicine contains 80 milligrams per 2.5 milliliters? Okay, now this is the same strength as what was in the last problem. 2.5 milliliters of this syrup contains 80 milligrams of drug. So if we can figure out how many milliliters is in this cup, then we can use that same relation, this relation again, to go to milligrams of drug. But this cup right here shows us teaspoons. The lines on the cup are teaspoons. Well, that's just great. We need to know what the volume is in milliliters. Well, it turns out that 1 teaspoon is 5 milliliters. Approximately 5 milliliters. It's not exact. So 1 teaspoon is about 5 milliliters. Okay, you can look it up. It might be like 4.99 or something if you look it up, to see what it is more precisely. But let's just say it's approximately 5 milliliters, and we don't know any more precision than that. So looking at the problem again, the problem is asking for how many milligrams of acetaminophen are contained in this cup. Okay. Now what we get from the cup is we can look at the marks and figure out how many teaspoons are in the cup. So the measured volume, if you were asking me, would be 2.5 teaspoons in this cup. You might say 2.4, I say 2.5. So 2.5 teaspoons are in this cup. So let's see if we can take 2.5 teaspoons and figure out how many milligrams of drug there is. Well, we know that 1 teaspoon is the same as 5 milliliters. So we can take our 2.5 teaspoons and, using this relation, turn that into milliliters. Okay, this relation builds that conversion factor. The teaspoons are canceled, and now you have milliliters. And then using the second relation, which is given to you in the problem, 2.5 milliliters is the same thing as there being 80 milligrams of drug. So we can put the milliliters down there, that gets rid of the milliliters, and then put the 80 milligrams of drug up there. So this is a two-step problem. And so 2.5 teaspoons times this conversion factor times that conversion factor should get us milligrams of drug. So you can handle your units. Teaspoons are canceled, milliliters are canceled, and you get to milligrams of drug. And then doing the numbers, 2.5 times 5 times 80 over 2.5. This is nice. The 2.5 actually cancels with that one down there. And so really the calculation is just 5 times 80, which is 400. So this is actually just a 1 sig fig result. Although you started with 2.5 teaspoons, which is 2 sig figs, we only knew the conversion between teaspoons and milliliters to 1 sig fig. So this right here is limiting us to 1 sig fig now. As soon as we take this 2 sig fig measured volume and we convert it to milliliters, that brings us down to 1 sig fig. Because remember the sig fig rules, 2 sig figs times 1 sig fig, you're going to have 1. And then it doesn't matter if you have the next relation has 2 sig figs and 2 sig figs. So that has already limited you to 1. So you do the math, and then when you get your answer, you only keep 1 sig fig. So you don't put that decimal point there. It's not 400 point or 400.0. It's just 400. And so that's a 1 sig fig answer. So kind of a complicated problem, but hopefully you're able to follow that. In our next lecture, we will cover density. So stay tuned for that. Aloha.